So hi everyone, I'm Katherine. I'm one of the TAs who are going to be recording regular discussion videos throughout the semester. And in general, I usually like to start off these videos with kind of a quick mini lecture on the topics that were covered that week and the topics relevant to the worksheet. But since this is like the first discussion section and the worksheet is pretty short and based on material that people have covered in previous courses like 61B before, I'm just going to dive straight into the worksheet. Oh, cool. So the first section of the worksheet is basically just a brief course overview of the different things you can expect from the course. And it specifically starts with a section about some questions you can ask yourself just to see like why you're interested in AI and what you want to gain out of 188. Other than that, the worksheet just goes over like kind of some distinctions in the course. So specifically, there are two types of discussion sections in 188. So the first type is regular discussion, which is what this video is. And then the second type is exam prep discussion. And so the differentiation between these two discussion sections are that regular discussions will go over the material learned every week and they'll kind of go through the basic concepts and then have questions to practice those concepts, while exam prep discussions will go more in depth and there mostly not be as much lecturing and more just like harder questions and more questions that you would more likely see on like midterms or the finals. So I would really recommend, just from personal experience, to try to watch the video or go to both types of discussion sections because they are quite different. So it would be a good way to kind of review both types, so both the concepts and kind of a more difficult level of the concepts. And then there's also a quick section that kind of notes down the grading distribution of this class. So specifically, there are 5 components to your grade, as you see here. And something that I want to note is that in general, your projects, which are the first section, the programming assignments, and your 2 types of homeworks will generally be quite straightforward. And because of that, these 3 sections are things that you want to try to get 100% on and just really understand and go through with. On the other hand, the midterm and final will tend to be harder and kind of like really test your understanding of the material. So that's why you want to make sure you maximize like your points and your grade by trying to get like full points on the other 3 portions of the grade. And I also want to quickly note, as I wrote in blue here, that with programming assignments, you will have 5 slip days total that you can use, but keep in mind that you can only use a maximum of 2 slip days per project. And then for both types of homeworks, there are no slip days, but you will get 1 drop for each type of homework, and that will be automatically added to your grade at the end of the semester. And also in this class, there is something called participation points. And participation points are not a distinct part of your grade breakdown, but it is something that could help boost you to the next grade, to the next bin in the future. So, and ways to get this participation is just all listed on Piazza. There's specifically a post about it, so please check that out. Cool, so now let's dive more into the material and the content of this discussion section. Cool. So this next question is based on uninformed search, and that is basically just a type of search where there is no extra information that the agent knows other than the structure of the tree or of the graph. So because of that, these types of searches become more kind of like brute force, where the agent is just trying and continuously looking until they find the goal. So specifically, the 3 types of searches are depth first search, breadth first search, and uniform cross search. So we are just going to start with depth first search and then just apply it on this graph. And something I also want to quickly mention first is that when you're describing searches, there are kind of these like 2 characteristics about searches that you want to keep in mind. So one of them is whether the search is complete. And that just basically means whether you are guaranteed to find a solution if one exists. And then the other characteristics you want to take into account is optimal. And if a search is optimal, that means that you are guaranteed to find the least cost path. So with each of these searches, we are going to ask ourselves whether that type of search is complete or optimal or both or none. So these are just some definitions that I want you to keep in mind. So now let's start doing depth first search on this graph. So something that I really want to know about depth first search and breadth first search first is that both of these types of searches don't care about the edge weights. So even though there are edge weights noted on this graph, you just can basically completely disregard them because they will just look for the next appropriate node, and then if there's ties, the ties will just be broken alphabetically. So no edge weights involved, at least for part A and for part B. And then specifically, depth first search will always look for the next steepest node, as I like to say. So because of that, for your fringe, you would want to have a stack. And that's the data structure where it's first in is equal to last out. So it's like you're continuously stacking that. So cool. So let's just start doing depth first search on this. And then specifically, I am just going to keep a running list of states expanded on the bottom. And yeah, let's start this search. Cool. So the first node, of course, we're going to look at is start, because that is our starting point. And remember that we're going to keep going until we get to the goal. Cool. So next, the children that start has are A, B, and D. And since we're going by alphabetical order, we want the first one alphabetically, which is A. So then we are going to expand to A. Cool. So even though B and D were the previous children start, since we're doing depth first search, we're going to continue going down the branch of A first. So then we can look at the children of A, and that's only C, which means we will expand to C. Then after that, same thing, we look at the children of C. And then we see that C has children D and goal. And just alphabetically, D comes before G. So the next one we're gonna extend to is D. Oops, wrong setting. Cool. D. And then we look at D, who has goal as one of its children. So then we're gonna expand to goal. And since we have reached goal, then we know to stop because we've already done our task. So these are all the states expanded. And then as you see here, we've only kind of explored one path, so that will be our path as well. So I can just quickly note it, and I would start, then A, then C, then D, and then goal. Yeah. So for this example, our path happens to be the same as like our states expanded, but that's not necessarily true. But something that is true if you notice with depth first search is that it will always kind of go down the left prefix of the tree, and then by tree, what I mean is like you can rewrite this graph in a way where you have start on the top, and then you can draw each of its node, and if you draw alphabetically, it would be like A, B, and D are the kids, and then A goes to C, and then C goes to D and goal, and D goes to goal. And then you can kind of fill in the rest of the tree as well. But in general, as you can see, the path we got is this left prefix of the tree. So that is a trait of depth first search. And then because of that, you can see that it doesn't necessarily find the most optimal path because it just always goes with the first path that is found, which is the like leftmost patch. So because of that, we can note that depth first search is not optimal. Cool, so we know that it's not guaranteed to find the least cost path, but is it guaranteed to find a solution in general if it exists? And it's actually not. So it is also not complete. And the reason why is that if there are cycles in the graph, then depth first search will just continue looping in that cycle, assuming that the goal is not in that cycle. And that's why depth first search is not always complete. It's only complete if you can guarantee the graph has no cycles. Cool. So yeah, so that is depth first search, and then this is our solution that we got. Okay, so now we are going to switch to talking about breadth first search, and just something that I want to reiterate is that you don't need to take edge weights into account for this type of search yet. So, but one difference with breadth first search is that your fringe is going to be a queue instead. And that's because you want to kind of expand to all of your children before going on to the next layer or the next like tier in the graph. So yeah, that's pretty much it. So I'm going to do the same thing and note a states expanded. And then, of course, we are going to start with the start node. And then for breadth first search, I find it easier to kind of like write down a list of like the running queue, so I know which nodes I've added into my queue and which ones I should explore next. So once we've explored start, it was added to the queue and then removed. And then when it was removed, the children of start also get added to the queue. And then we want to add them in alphabetically because that is how we are breaking ties. So the children of start, just like how we noted up here, is A, B, and D. So we would want to add in A, B, and D. Cool. So now we want to see who next to explore. And the next one on our queue is A. So we would expand to A. And since A was removed from the queue, then we also want to add A's children to the queue, which is C. Cool. And then next, we would explore B. So pop B off the queue. And then we can add B's children to the queue, which is D. But D is already in the queue, so you would not need to add it again. Cool. And then next, we have D. So I'll do the same thing. Explore D. And keep in mind that was the original connection, not the one from B. And then you can add D's children, which is goal. And then next you would explore C. D has already been explored and goal is already in the queue. So you would just not add anything, and then the last one you would explore is goal. And then that was added from these paths. Cool. So then based on this, you can see that our resulting path is this path. So specifically, it is start, D, and then goal. And then yeah, that's it for our breadth first search. So now let's analyze the characteristics of whether the search is complete or optimal. So in general, this search is complete because it looks through each layer and then it considers like kind of all branches before moving on or like taking the next step in the path. So that's why breadth first search is complete. And however, it is not optimal. And that's just mainly because it doesn't consider any edge weights. So because of that, it's like kind of similar in the idea that it just finds the kind of first path that is satisfied instead of like the best path. And we will actually see a more optimal path in part C. So yeah, so that is it for breadth first search, and these are our answers for these parts. Cool. And then let's move on to the last part of uniform cost search. So now with uniform cost search, we are actually considering the edge weights, and because of that, we always kind of want to pick the cheapest node that's in the edge next. And that's why we then want our fringe to be a priority queue, so that every single time we kind of like take a node from this fringe, we are always taking the next least cost node. So same thing, I am just gonna have a states expanded list here, and we are going to start with the start node. And then since this is a priority queue, I am also going to just like kind of have a running list of the different values I'm keeping a track of, but I won't necessarily be like pulling from the front or the end of the list. I'm just gonna like look through and then find the minimum. So yeah, so let's start. So we have expanded to start, and then now start is no longer in our fringe, but we add the children A, B, and D as before. But specifically now we want to take edge weights into account, so I'm just gonna write it as A2, and then let's see, it was B3, oops, not C, B3, and then D had weight 5. Cool. So looking off of this, I can see that A has the shortest edge weight, so we are expanding to A next. Cool. And then we can, because of that, A is no longer on the queue, but then now we have to add C. And C's weight is going to be 6, and that's because you want the weight from the start. So you have the edge of length of 4 plus A's original weight, which is 2, so that's why you get 6. Cool. And then from here you can see that B is the next one with the least weight, so you would want to explore B next. And then with B, you technically add D to the queue, but D is already there. So what you need to do is compare the weights and see if you can update the weight with like a closer or like a smaller value. But here you can see 4 plus 3 is 7, which is greater than 5, so no updating is necessary. And then next you can see it is D who has the next least weight. So then you would expand to D. And then you can add goal. And then for goal, you have 5 plus 5, so 10. Goal. And then next you have C. You're expanded to. And then with C, you can add goal. And you see that you have 6 plus 2, which is 8. And that's actually less than 10, which is the current value of goal in this priority queue. So what you actually want to do is you're going to change this value of 10 to 8. And there's not as necessarily as much effect right now because node order change is different, but it will affect the ultimate path you pick. So then now you see that the last one you have is goal, so you will just explore goal. Cool. So now you have explored everything, and then from here you can see that your path to goal is actually going to be this top path, not the same path that you found in breadth first search. So specifically the path is going to be start, then A, then C, and then goal. Yeah. So that kind of shows how when you take weights into account, it can be different, and that proves how breadth first search is not optimal, because in the same graph we found a more optimal path of length 8 versus length 10. So based on that, uniform cost search is complete and optimal as long as there's a finite path and no negative edges. So those are just kind of some conditions that you want to keep in mind, and we'll later go on to how to deal with negative edges. But in general, those do not come up as much. And yeah, so that's it for uniform cost path. This is our solution. And that wraps up this discussion section. I just want to say thanks for watching this video. I hope you watch my future discussion videos too. And yeah, I hope you enjoy 188.